Alright, so we're looking at problem 4 from this European Girls Maths Olympiad. Okay, so the first part of this question, we're going to want to try and draw a diagram. Yeah. So has everyone drawn a diagram?
Yeah.
Okay, so there's a few things you might want to know what they mean. So like in center, there's circumcircle, parallelograms, and concyclic. Yeah. Okay, I think I saved some time. So the one benefit of a walkthrough, I guess, is I already drew all the diagrams and stuff. So you find it's easier to draw the circle first, okay? So the circumcircle of ABC is the circle that passes through A, B, and C. Okay? So one thing you'll learn when you draw the diagram is it's easier to draw the circle and then fit the triangle and stuff inside than to fit the triangle and then draw the circle afterwards. Okay? Okay, so then um so that's the circumcircle. Yeah, so you can basically draw infinitely many triangles and it sort of suffices for the diagram. Whereas if you drew the triangle first, there's only one circle you can draw. Okay, and it's hard because it's curved as well. So, okay, so we know what that is. And then, so the incircle is defined to be, it's kind of like the dual of the circumcircle. It's got to do with the sides of the triangle instead of the vertices. Okay, so it's tangent to all three sides. Um, so maybe a practical definition which you can prove is the incenter occurs where the angle bisectors meet. Does that make sense? So the angle bisector is kind of like the internal one is a line that's sort of halfway between these two lines. Okay? And if it's halfway between these two lines, then any point on the line must be equally distant from those two lines. Okay? And so a point that's equally distant from all three sides lies on both angle bisectors. Okay. So, and then in the question, the angle bisectors get extended to the circumcircle, right? Okay. Then you get points P and Q, and we have S and R are then defined next to be points that make PAC a parallelogram, and R is a point that makes BAQ a parallelogram. Yeah. Okay, and then lastly T is it's where SC and BR intersect. Okay, and then the problem asks, so I drew the points in black, so SITR, right? Prove SITR lie on a circle. Okay, so does that make sense? Are there any questions about this? No? There might be some points of background. So one of them, I guess, is the angle bisector thing we already said. So we can assume the angles here are the same. So we can assume, like, say the angles here are the same, for example, right? And the angles here are the same. Okay, so do I need to remind people what concyclic means? So as far as we're concerned, ways to show things are concyclic is, so if something lies in a circle, then we have this thing called the bow tie, which says these two angles are equal. Yep. And conversely, if you have just the bow tie, it also shows it lies on a circle. Okay, so if the angles are equal, it lies on a circle. Or basically the same kind of theorem is if you have a quadrilateral, these two add up to 180, if and only if it lies on a circle. Okay, so we might just call this like cyclic chords. Okay, I'm kind of assuming you guys know like what similar triangles and stuff are, right? Okay. So then I guess the first part of the question is tell me what the points P and Q are. Okay? So that's kind of our first little goal. And we got someone outside basically solving this problem. So let's see how long they take to finish compared to us. Okay, so before we start sort of doing anything with angles, let me sort of just ask you where are the points P and Q? Okay? So I'll give you a few minutes to tell me and then I'll explain it. So basically,
Here are the midpoints of a arc AC and arc AB.
yeah, there you go. So basically what Audrey says is right. So because these angles are equal, right, then Q has to lie in the middle of the arc AB. Okay? And the reason is because of like, it's kind of like that bow tie thing. The bow tie says that the angle, you can move the angle around, but it stays the same, right? So the angle only depends on the arc that it stands on, okay? And so if you have an equal length arc, then it should make the same angle, sort of by symmetry, because you could rotate this arc over here, for example, right? Okay, so the point P lies at the middle of the arc AC, and the point Q lies in the middle of the arc AB. So we kind of know exactly where P and Q are. Okay? And maybe just to get our notations together, let's all agree to call this angle here. Let's all agree to call this angle here gamma. Okay? And then this angle here is also gamma. Let's call this angle here beta. And this angle here is also beta. Okay? So this is also beta. Yeah? Okay. So we basically know what P and Q are. Actually, you notice it's kind of nice to have basically all the points in the question, like all the blue points are on the circle, and then the black points are the ones that we want to prove. Um, we actually have a complex bash of this on video for the more advanced students. You can look for the video. Um, I can send you the link or something, but I guess so naively trying to show that four things are cyclic, it has something to do with an angle condition, right? So maybe the next exercise is to find as many angles as possible. Does that make sense? Okay, try to find as many angles as possible. And then I'll check up how you do in a couple of minutes, because there's a specific way I want you to find the angles, but I want to see if you can do it anyway. Okay, so I might add some conditions to what I want, so just in case you haven't figured it out. So I want you to label the angles, but not just randomly. I want you to label them in terms of beta and gamma. Okay. So those are the ones we decided to start with. We kind of hope not to introduce more notation if we can avoid it. Yeah. Okay. So I want you to tell me as many angles in the diagram as you can in terms of beta and gamma. Okay. So you might call this angle chasing or maybe angle bashing. Okay. Yeah, so there's at least 10 angles you can kind of try to find, and maybe I'll give you an example of one of them just so that you kind of get the idea of what I'm going for. So can you see that like this angle here is equal to beta because it's on the same bow tie as that, you know? Okay. And I want you to find other angles kind of like that. There's at least 10 of them. I'll give you at least 10 minutes, okay? Alright, let's start finding some of these angles and see if you guys got the same thing. So, so Audrey seems to have marked in this one, which is like almost like one of the final bosses. This, so we're labeling these as gamma, right? This is beta. Yeah, so this is 180 minus gamma and beta. This is beta. So I was hoping you'd see this interesting one because this is what makes use of the parallelogram. This is a beta. Yeah. Okay, and then this is 2 gamma. Like if you didn't do this on this side, you could just do it again on this side, right? So it's the same thing on the other side. So here you have gamma. Yeah. This is gamma. And then you kind of know that this is sort of 180 minus 2 gamma minus 2 beta. 5. This might be counted as 2 beta. That's 6. And then if you count these ones here, it's like 180 minus gamma, 180 minus gamma. That's like 8. So Audrey marked in this was 180 minus gamma minus beta, right? Did anyone find like this angle here? Okay, so maybe the next thing you can do if you haven't done it already is find the angle at T, okay? Okay, so yeah, so you notice this angle's gamma, this angle's gamma, and this angle is also gamma because of corresponding angles. And similar reasoning shows you that this angle's beta, right? So if you know that that's beta and that's gamma, then you should be able to work out what T is. You know? Yeah, there's sort of lots of ways to figure it out, right? Because, I mean, so if you know that that's beta and that's gamma, right? And that's 2 gamma. So this is 2 gamma minus beta, right? Yeah, so then the angle at T is 180 minus 2 gamma minus beta minus 2 beta minus gamma, right? Yeah. So another way to think of that is, I mean, the angle between the red line and the green line is also the angle between this green line and this red line, right? And that angle here we know is 180 minus 2 beta minus 2 gamma, 2 gamma minus 2 beta, and then this is gamma and this is beta, right? So either way, you get the angle at this to be 180 minus gamma minus beta, you know? Okay, so my question is, what does that mean? So it's a short question, but what does it mean to have that angle be 180 minus beta minus gamma? Okay. So I'll give you 1 minute for that. Alright, so the thing I wanted you to notice is that the angle at T is actually equal to the angle at I, okay? Which means that CITB lie on a circle, okay? So in our live solve, we kind of went down that route. It does eventually lead you to the right thing, maybe a little bit less directly. But in this walkthrough, we're not going to go down that route, okay? So if you want to see what happened in the live solve, you can watch the video. But roughly what happens is sort of because there's a circle, um, you get some interesting things that happen if SITR is also on a circle and you have the intersection of two circles, they intersect at I and T, okay? But we're gonna stick to a more basic approach. See the thing about junior is that juniors only usually has one circle, okay? So the other one you might think is more intermediate. There's more circles. Okay, so now I want you to. So we got basically all the angles we can hope for, right? Maybe we're missing a couple, okay? But so in terms of the angles we have, okay. So look at the angles that we need to make the bow tie work for SITR, okay? And see how that relates to the angles we have. That make sense? Okay, so that's what we're going to do. So we had two options. One was to investigate CITB being a circle, but we're not going to do that. Instead, we're kind of just going to go straight for the kill and see what happens with the angles that we need in terms of the angles we have. Okay? I'll give you a couple of minutes for that. Okay, so one problem you might run into is like I is not connected to anything, right? So to get angles, like you might have T, like this one's already good. Its T is already making an angle with S and R, right? But I isn't, so you might want to draw in so that I can go into S, it can go to T, it can go to R, right? You could also join R and S, but so yeah, I feel like if you join R and S, you're gonna have to find more angles. Let's just deal with these ones for now, okay? Do you notice anything about these angles? So for example, you could try to get a bow tie with this angle and this angle, right? Um, yeah, but since you know that the angle at I is the same, that's kind of like getting this angle and this angle, yeah? Or you could get on the other side, you get this angle and this angle, yeah? Okay, I'll give you a little hint, okay? This is actually not necessary to know, but this is more along the lines of what we did in the live solve. So the hint here would be find this angle. What's the value of this angle? And what's the value of this angle? Okay. So those are angles that we could have from before. So what are those angles? Okay, so there should have been two things. You'd actually calculate those light blue angles and then make an observation, okay? So there's lots of ways to do it. For example, here we have this is gamma, or is it gamma or beta? Beta. And then this is 180 minus beta plus gamma, you know? Here we have I don't know why it's a bit weirder, but Yeah, so TBI is beta minus this angle, and this angle is gamma. Yeah. Yeah. This is gamma, this is gamma, and then this is beta minus gamma, yeah. And then this is 180 minus beta minus gamma, so it's plus gamma like that. Yeah. And then if you do it like that right next to each other, then you hopefully will notice that they're actually equal, right? Does that make sense? Um, yeah. So I guess the goal of the exercise is kind of to focus you on the triangle SCI and the triangle IBR. Okay. So if you look at these triangles, let me just highlight them. Maybe in purple. So this triangle here, and this triangle here. Yeah. So what's interesting about those triangles? Well, first of all, we notice that, remember we wanted this angle to be equal to this angle for the bow tie, right? Well, for that to be true, you need this angle here to be equal to that angle here, right? Yes? Okay. Another angle we wanted to be true for the bow tie was this angle and this angle, yeah? But notice, even though they go to T, they actually only depend on the first part, at B and C, okay? And the third angle in the triangle actually also happens just to be true, equal, yeah? Okay. So maybe, so in terms of the two purple triangles, sort of, can you explain to me what our approach could be from here? Yeah. So, what is it that about these purple triangles that we notice, and how? Okay, good. Well, sure. Okay, and then how do we use that to proceed from here? Okay. Yeah. So you already noticed that they have the same angles and they're similar, right? Okay. So how do we take advantage of noticing that they're similar to proceed? Okay, that's the question. So I'll give you a couple of minutes for that. Yeah, so I could have let you have a long time for this question because essentially, like, a lot of problems are basically solved with this idea. Okay, so what you have is, so let me try to explain the situation to you and how we can get out of the situation. Okay, so we're trying to prove basically any of those angles are equal, except for the light blue ones, which we know are equal, right? Huh? Yeah, so you got to be careful with what's being said. So what we're saying is, so if those angles are equal, then we have a bow tie and then the 4 points are cyclic, right? So we don't actually have that the angles are equal, but we would have the angles are equal if the statement's true, right? So um, so if the statement is true, we actually get a little bit more than just the angles are equal, right? We get that these triangles have to be similar. Does that make sense? So so we have similar triangles that kind of um, so that's equivalent to our statement being true, right? And at the same time, we have sort of like a difficulty in getting any angles to be equal, okay? So we might get the light blue angles to be equal, but it's not so easy to get the orange angles to be equal, okay? So especially because you kind of just drew the line in, and see, the angles are created by like a new line, and then it's hard to figure out sort of where that line is in comparison to everything else, relative to everything else. Okay. So I don't know if there's a name for this, but personally I've called this an angle blockade. Okay. It's because you know, a lot of questions in geometry are done by just chasing angles. So it's like you're chasing the angles, but now there's a blockade. Yeah, something stopping you from just chasing angles. Does that make sense? Okay. But having these similar triangles helps you get out of that angle blockade, okay? Because so you can prove triangles are similar in like how many ways? Yeah, I guess more than one way, right? So one of the ways to prove triangles are similar is to show two angles are equal, right? Is that going to be the way that's going to help us? No. Okay, so the reason is we want to conclude the angles are equal, right? So if we prove the angles are equal to prove it, then we might as well just prove that the angles are equal in the first place, right? So if we really want to take advantage of the similar triangles, we'd use one of the other conditions to prove the triangles are similar, and then conclude the angles are equal to solve the problem. So now we need the side lengths now, right? Okay, we only have angles, but um, surprisingly enough, we actually do have some side lengths. Now the question is, if we were to prove these triangles are similar, which side lengths would you try to show are related? So you have three sides in a triangle, yeah? So my question is, which side lengths would you try to show? Okay, which one? Okay, so think about this. There's basically like you can either do all three sides or you can pick two sides, right? Yeah. So I'll give you 1 minute to think about what your options are, okay, and then tell me what you think you should do. Okay, see if you kind of just restrict yourself to doing similar triangles, you don't have that many options, right? See, you could prove triangles are similar by showing all three sides are proportional, right? Or you could prove that like two sides are proportional and one of the angles is equal, right? So if you could prove two sides are proportional, why would you prove three, right? So you can see that because you have this angle here, you can prove these two sides and not three, right? Okay. And if you were to pick two of the three sides, which ones would you pick? Well, if you only had this angle, then you'd have to do these two, right? But at the same time, you would kind of think to pick those anyway because they're the ones that you already have in your diagram, right? Whereas SI is like one that you drew in, right? So that's going to be more mysterious. The IR is also the mysterious one, right? So actually, if you can prove that SC and BR are in the same ratio as IC and IR, right? Then that would solve the problem, okay? And those are things in terms of things that are already in the diagram. There was another observation I probably should have included earlier, but you probably already noticed this subconsciously, if not consciously. Um, Focusing on the similar triangles now actually deletes the t, right? There's no need to consider t anymore. You know? So it's actually a pure simplification. So you can actually think of this problem as no longer involving t. Okay. Um, okay, so now that you know what you're trying to do, okay, so you want to show that SC and IC are in the same ratio as RB and IB. Yes, how would we give them ratio? So maybe don't jump the gun too much. Let's try to find some simplifications, okay? Find some simplifications and then we'll get started with the ratios, okay? All right. So I'll give you a few minutes to find some simplifications. Okay, so if you remember the triangles, we want to show this side here. I'll put that in purple. has the same ratio to this side, right, as the green BR has to the red CS, right? Yes? Yeah, no, that's what it means to be in proportion. So IB over IC equals BR over CS. Yeah? Okay, that's what we want to show. Okay. But the whole point of, say, look, so the green, right, is actually, it's a parallelogram. So BR is actually equal in length to AQ, right? So the CS is also equal to AP, right? Yes? So you can actually delete, um, you can delete R and S, yeah? Because you only care about the ratios of the red and green, right? So you can focus now on this red length, right? And this green length. Yeah? So we can delete all of this stuff. Yeah? That makes sense? That's like a simplification, yeah? Okay. Yeah, so we can delete the T. So it's just the triangle and the angle bisectors now, yeah? Um, CI and PA are not parallel necessarily. So mhm. Okay, so I'll give you a moment to digest this. So try to draw a new diagram with just this simplified data and see what you get. Okay, I'll give you a few minutes. Okay, you guys are gonna be like, oh, that's what he was talking about. So we've simplified it to this diagram now, right? Okay, deleted the R and the S, deleted the T. Now everything's in this nice circle, okay? The thing I wanted you to notice was this. So remember, P is in the middle of AC, right?
Yeah.
Yeah. So that means these chords are going to be of the same length. Yeah.
Yeah.
Yeah. Yeah, we talked about that, remember?
That means AQ is equal to QB.
Yes. AB. You mean QB?
QB, yeah, that makes sense. Oh.
Yeah. So like, the point is, I don't need to draw these because they're the color coded already, but the point is like, it depends on where P is, it depends what Q is, right? And at the start we realize they're in the middle, yeah? So they're in the middle, it means they're the same, yeah? Why is that helpful? Why is it helpful? Yeah, so why is that helpful? Well, now you can actually maybe that would be the next question. Why is it helpful? Okay. So why does making these so we're doing a change of lengths now, right? So instead of doing those red lengths and those green lengths, we're now doing this red length and this green length, right? How is that different? How is that helpful? Yeah?
Bow tie. Oh. Bow tie. Oh.
Okay, so you guys got that pretty fast. Yeah, so now the difference is the colors, the purple and the red are in the same triangle now. Yeah? The purple and the green are now in the same triangle, okay? So now you can try to prove those triangles are similar, yeah? Yeah, so let me try to draw this triangle with what color? Yellow. So now we have this multicolored triangle. It's similar to this other multicolored triangle, right? And but you can actually prove that now, right? That's the difference. So can you prove those two triangles are similar? Yeah, so those angles are equal by bow tie, yeah? And then, these angles are equal because they're vertically opposite or something, right? That proves they're similar, yeah? And that means the ratio of the red to the green is the same as the purple to the purple, right? Okay, can you see how it all fits together now? Do you have any questions? That's pretty neat, right?